How's it going? My name is Ryan Rad. I'm an electrical and computer engineer, and I am the team lead.
Hi, my name is Mohammed Al-Yamani. I'm an industrial engineer and I'm the procurement lead.
Hello, my name is Cole Rogers. I am an electrical and computer engineer, and I am the software lead on this project.
Hello, my name is Esteban Salazar. I'm the materials science engineer, and I'm the materials lead.
Hi, my name is Roman Sharp. I'm studying industrial engineering, and I am the industrial lead.
Hello, I'm Devin Taylor. I'm studying mechanical engineering, and I'm the testing lead.
Hello, my name is Allison Williams. I'm an aerospace engineering major, and I'm the design lead.
Hello everybody, we are Team 25047, and today we're going to be talking about our project, a 3D printing filament temperature and humidity storage box, also known as the oven. Before we get into that, the team and I would like to give a special thanks to Raytheon here in Tucson and the Bike Shop for sponsoring this project. The Additive Manufacturing Lab at Raytheon here in Tucson produces thousands of 3D printed parts a year of varying material and scope. Most of the 3D printing filament used in the printers have different temperature and humidity sensitivities. For example, metal filaments need to be stored at high temperatures before they're printed with, and most filaments need to be stored in dehumidified, low humidity environments. Raytheon's current storage solution is to use dry boxes with silica gel packets to try and preserve the humidity levels of the filament. This storage solution causes wasted filament due to improper storage over time and extends lead times on metal prints as they need to be preheated before they can be used. To tackle this problem, our team developed a special heating and storage chamber that will house a large volume of spools. This chamber can be set to different temperatures by the user for different types of filaments. With this solution, the bike shop will have a central location for the spools, be able to preheat filament to save on time, and will waste less filament due to the low humidity of the chamber.
Okay, Allison, so tell me a little bit about how the design came to be and what were the biggest challenges?
The design itself wasn't too complicated. It consists of 3 sub-assemblies that come together to make the final assembly. The biggest challenge was navigating how to best design the system while meeting each of our requirements and staying within our budget of $4,500. For example, the chamber where the spools of filament are going to be stored has to have enough volume to store 30 spools of filament. Our system also has to have enough structural integrity to support 500 pounds of weight on the top surface and have enough room to fit our insulation and electronics. These requirements, coupled with time, budget, and manufacturing constraints, made it very difficult, and I ultimately had to redesign this project around 10 times.
All right, Devin, can you give us a bit of insight into how the structure was made?
Okay, Esteban, let's break that down. The structure was very important since not only does the project need to support its own weight, it also has to support the weight of the printers being stacked on top of it, per the requirement. This led to the design decision of welding our structure into a solid frame which could support more than enough load and not be damaged while transporting. To make sure it would work, since welding would be a permanent step, I ran many different types of FEA simulations and did some calculations myself to ensure that at no point would our project structurally fail.
So, Cole, to the uninitiated, they wouldn't suspect a software involvement in this project. Can you tell us a little bit about your work?
Sure. I guess I could start with one of the requirements being that the system would have a user interface. This got the ball rolling into how hardware and software would be incorporated into the project. First, we needed a touchscreen for the user inputs. Then we needed a microcontroller to relay these inputs into the heater based on the data read from the chamber environment from multiple sensors. Finally, all of these operations needed to be relayed back to the user. Now, all of these things require programming to work. To ensure the code worked properly, we tested it in a simulation called WalkWe, which simulates the software running on simulated components that would actually be used in the end design.
All right, Roman, so what kind of testing was done for this project?
While I can't speak for the methods of other projects, our project was unique in that it wasn't just a prototype or a continuation of a previous project. Our project had to work for its intended purpose the first time, and so all of the designs and tests were made from the ground up. Most of our testing was done with simulations. We simulated the system's structural capabilities, its thermodynamic behavior, and how the software and hardware would integrate with one another. We couldn't afford to iterate this design, so we pushed these simulations to the limits to give us a large safety margin for when we actually built the system. During the construction, we tested all of its physical features, such as its structural integrity and mobility, and verified most of the system requirements. At the time of this video, we were finalizing testing the last requirements.
Okay, Mo. So I understand that this project came with a budget. How did you manage it, and were there any obstacles?
I feel with this project and almost every other project, things never go exactly as planned. For instance, at the start of this project, the team didn't really have a clear vision of our final design or its feasibility within our budget and timeline. So to save on money, the team did extensive research into every component of the project to find the most reliable parts within a price range that would give us wiggle room for other parts and unforeseen problems later down the line. Even then, it still wasn't enough. So to save on budget, our team spoke with our sponsor to redefine our scope and requirements, which helped us redesign our project to the form it is today.
Alright, Ryan. To some, when they think of a sealed hotbox with running currents, they think it could lead to some kind of disaster, especially when it's designed by students. Can you tell us how you made sure that this project poses no risk to anyone?
Yeah, absolutely. Safety was always a priority in this project, not just to the user, but also to the facility it's housed in and the filament that's being stored in it. And we put a lot of time and effort into ensuring that this project would be safe on all levels. Starting off with the physical side, our project uses a PTC heater, which means the heater has a physical upper limit on how hot it can get, even if the current and voltage are constantly applied. Second, we've implemented a circuit breaker in our project, protecting the user and our electrical components in the case of a shorted or overdrawn circuit. Third, we have also implemented an emergency stop button to allow the user to quickly shut down the system in any dangerous situation. Fourth, the system has 3 redundant sensors that regularly check the conditions within the chamber. If an error condition is detected, the system will shut off.
Here we see our buddy Devin, seeing the project for the first time being delivered to his lab. Now, with the oven in hand, Devin here is going to push it to a designated spot on the floor. Look at him go. Now in place, Devin knows he has to place 3D printers on top of the oven, so he's going to check if it's level. Uh-oh, looks like the oven isn't level. Luckily, Devin came prepared. He has access to the operator's manual, which will show him exactly how to adjust the casters at the bottom of the oven to make sure that the whole system is level again. Devin checks again, and would you look at that, it's level. Now that the system is level and in place, Devin is ready to plug in the power cord to a 120 volt outlet to power up the oven. Now powered up, Devin is going to access the user interface. First, he's going to set it from Celsius to Fahrenheit. Oh wait, looks like he's going back to Celsius. Next, he's going to set it from 30 degrees to 45 degrees Celsius. And then he's going to hit start. This will activate the system, getting it ready to go to temperature. Now heating up, Devin is going to go grab one of his filament spools and place it on the racks. Next, he's going to close the door and he's going to wait an hour. Now that the hour has passed, Devin's going to reach inside, grab his spool, and would you look at that, it's prepped and ready.